Good morning, everyone.
Good
Good
morning.
morning.
Hi, my name is Mehdi Shukriyan. I'm an assistant professor in the Department of Civil Engineering, and I'm going to start my presentation. Is that still, you still have 1 minute? Okay. So you see my screen and,
Yes.
okay, great. All right. My name is Mehdi Shukriyan. I'm an assistant professor from the Department of Civil Engineering, Morgan State University. And the topic of my presentation today is sustainable design of concrete bus pads to improve the mobility in Baltimore City. In this presentation, I'm going to talk about some introduction about the bus pad and bus pad design, the problem statement, which is based on the case study that we did in Baltimore City bus pads, talking about the methodology that we want to use for design and evaluating the performance of bus pads in Baltimore, and then results and discussion following by the conclusion and recommendation. So then we're going to talk about the future works. Bus pads as a part of an urban pavement play a vital role in infrastructure sustainable development. However, in many cities, they are in bad condition and perform poorly. So the bus pads defects can decrease the road safety and increase the maintenance and transportation costs, which are very important. So in assessing the in infrastructure, the assets management. So the 5 main factors were identified as a reason for bus pads deficiencies, including the environment, structure-related deficiencies, construction, maintenance, and traffic. Bus pads deteriorate over the time due to the effect of the stresses caused by traffic and environment. How a bus pad responds to these stresses will depend on a bus pad structure, such as a material type, layers, thickness, type of the reinforcement that we want to use, subgrade properties, of course. And in addition to that, the construction characteristics, including the construction technology, quality of the construction, and maintenance are very important as well. So the treatments that applied for the maintenance and repairing the concrete bus pad as a rigid pavement are also very important. And the method that we want to use to do these repairs are also a main factor to considering and evaluating these deficiencies. The bus pad performance at a certain time of a service life can be characterized and assessed in terms of the particular distress or a combined index that represents the bus pad's overall condition. The factors involved in determination of the bus pad condition are material type and distress observed. So in both cases, performance indicator reflects the bus pad's condition at a specific age of the pavement service life. It's important not only to understand the current condition of the bus pads, but also how their condition will change over time. This is a typical deterioration of the rigid pavements that we consider basically in 4 different phases. So the first phase of the deterioration is called a slow phase. That is for several years that the pavement experiences a slow deterioration process, particularly in the surface, and also though to a lesser degree the rest of its structure. The deterioration rate depends on the quality of the initial construction. To stop this process of deterioration, it's necessary to apply with some frequency various maintenance treatments, mostly on pavement surface and drainage works, which are very important, and especially in phase A and phase B. The group of these maintenance activities is defined as a preservation and should be performed as a part of a routine maintenance. The second phase, phase B, is an accelerated phase, which after several years of the use, the pavement enters a stage of accelerated deterioration. At the beginning of this phase, the basic structure of the pavement is still intact. The surface distress is minor, and the common user has the impression that it still remains in a good condition. However, it is not. Going further, in phase B, more damage to the surface is observed and the basic structure begins to deteriorate, which is not visible. These distresses begin as a punctual and slowly spread until eventually they affect the most of the pavement surface. This phase is relatively short. Once the surface damage is widespread, destruction is accelerated at the start of this phase. Reinforcing the pavement surface usually is sufficient, so maintenance is relatively low cost. So it's the best time to do the maintenance and do the action in maintenance plan in phase B. Once a sustainable reinforcement is applied, the pavement again is suitable for function and can withstand the traffic for many more years. This type of activity is defined as a functional maintenance or simply maintenance. In phase C, after the accelerated phase, the optimal intervention time passes, and the more the intervention is delayed, the greater the damage and the higher the repair cost. The damage that occurred in the basic structure of the road must be repaired, which means demolishing and lifting the damaged parts, replacing the components with the new ones, and then reinforcing the road surfaces, which is mainly costly. This group of activities is frequently named structural maintenance or rehabilitation. When it refers to the combination of the partial repairs on the basic structure of the road and strengthening its surface. The phase D is a decomposition phase. When no intervention are applied at any time in previous phases, the pavement reaches the point of the breakdown and failure is widespread for both pavement surface and basic surface. Decomposition of the road is last stage of its existence and can last several years. At this phase, the only solution is reconstruction of the pavement. There is no maintenance plan efficient for this phase D. Based on the deterioration stages, Based on the deterioration stages, it is essential to consider maintenance activities for each stage to optimize the resources and extend the service life of a pavement with a good condition. And as I told you, the phase B is the best phase and best time for taking action on maintenance plan. So regarding the typology of the cracks and defects and the causes of these cracks, so the concrete boss pads are basically considered as a rigid pavement. So we have two types of pavements, flexible pavements like asphalt and rigid pavements, so which mainly considered as a concrete pavement. So as a rigid pavement in design and repair methods, so we need to be very careful when designing the rigid pavements, so which basically use a material of concrete, and similar concern that we have in terms of the defects and causes of these defects for the rigid pavements can be applied for boss pads. In addition to the type of the load that we have more frequent load and repeated load over the time, and the fatigue load need to be also taken more seriously than rigid pavements. So when it comes to the repair of distressed concrete pavements, few options are available. It's very difficult and time-consuming to repair the hardened concrete. Full depth and partial depth repair, slab replacement, crack sealing, crack stitching, and staple pinning are some of the techniques that can be used to repair the distressed concrete pavement. So some of these type of cracks that I want to mention here, so a couple of them are listed here. So as a settlement cracks, so settlement crack is basically when a subgrade or subbase can cause the cracking of a concrete pavement due to the settlement, and the crack resulting from the settlement of the subgrade are normally variable in direction, but most commonly appear diagonally and extend continuously to many slabs. So repeated heavy truckloads may cause a further breaking of the slabs into several pieces due to the loss of the support beneath the slab. Like all materials, concrete also expands and contract with the variation in temperature. So the concrete shrinkage, which basically due to the temperature at the early age of the concrete, is also very important to be considered. So the concrete slab cracks when tensile stresses within the concrete overcome the tensile strength. At the early age, the tensile stress develops from the restraint of the concrete volume change or slab bending from the temperature and moisture gradient through the concrete. And these can cause the major cracks, so that need to be considered in designing of the concrete or rigid pavements. Another thing is the weather, that the weather almost always has a role in occurrence of the uncontrolled cracking. Air temperature, wind, relative humidity, and sunlight all influence concrete hydration and shrinkage. These factors may heat or cool concrete or draw moisture from the exposed concrete surfaces. So other different type of the cracks are listed here as a blow-ups, cracks over the dowel bars, and the surface pop-outs, and curb cracking. The surface cracks were observed on concrete bus pad designed for Baltimore City. So this, as I told you, this is a case study that we did in Baltimore City and several bus pads. So based on the observation and tests that we have done on these bus pads, and try to identify the causes of these bus pads, since we wanted to figure out how we can come up with a solution to mitigate or minimize these surface cracks over the time. So therefore, the main objective of this research is to identify the critical loading scenarios. Basically, we try to use a different methods to design the bus pads. Through that, we try to see what would be the critical load that need to be considered for design. And second also, we have to evaluate the structural responses and assessing the deficiencies that we have based on the current condition and existing design. So at the end, so the last objective is to present a recommendation to enhance the current design and propose a new design for concrete bus pads in Baltimore. The design parameters for three bus categories: large bus, mid-size bus, and articulated bus were studied. Other small vehicles may also be used for transit services, but generally their characteristics are not critical in designing bus pads. Federal weight regulation for commercial motor vehicles, CMV, are applicable to interstate highway and 160,000 miles of other major roads. So the state and locally controlled roads often have separate regulation that differ from the federal regulation. So As you see in the table, all of the the states are listed with their the limited weight for the buses that they have. So we studied all of those, and then we also compare these with the load that is recommended in AASHTO, so that we'll be discussing next slides. There are two methods for pavement design. The AASHTO pavement design guide, which was basically based on the field testing of flexible and rigid pavement structure, and was started by testing in Ottawa and Illinois in late 1950 and early 1960. So this empirically based pavement design procedure is used by many practicing engineers worldwide. The AASHTO guide is based on the performance of the test section under the truck, traffic, and environmental condition. One major output of the AASHTO road test was the load equivalency factor. So,
Yes, Dr. Gianni. Hello.
Which is LEF concept. And LEF concept were used to quantify the damage different axle loads and configuration caused to the pavement relative to an 80 kilonewton single axle load. So this was basically a pavement design method that has been used widely for rigid pavement especially. And then the latest version of the Portland Cement Association, or PCA, is another method that is used for the design of a pavement, particularly rigid pavements. So the PCA thickness design for concrete highway and stress pavement have more mechanistic features than the empirically based AASHTO guide. So the PCA used the load spectra analysis to calculate the bending stress in concrete due to the variation axle loads and configuration. Load spectra analysis is more theoretically sound than ESAL that was recommended by AASHTO. And analysis, because of the fundamental stresses and strain, are calculated and related to the performance of a laboratory concrete fatigue beam test. Load spectra analysis also allows for calculation of a pavement stress due to an axle load and configuration not originally considered in AASHTO road test. And the PCA guide also has many limitations, such as not taking into account the temperature stresses in the slab and no ability to analyze the widened lane or different joint spacing. Also, the top of the base K value concept and no consideration of the load transfer across the shoulder is another limitation of this method that basically presented. So in this research, we use a numerical method and we employ a numerical method to obtain the critical internal moment and forces, as well as experimental study for assessing the existing design of the bus paths in Baltimore City. So the soil and slab stiffness were taken into account, and more realistic methods to apply the moving and temperature loads were used to analyze the load distresses and soil pressure and the slab strength. The load that was considered in the numerical model was based on the HL93 in AASHTO that was compared with the limitation of the buses that are basically listed in the table that I showed earlier. So after the study on these, we found that this equivalent axle load can be considered by considering the tire contact area for the trucks, and with combination of a tandem load So with the lane load that was recommended in AASHTO, so we started performing the computer simulation and modeling the bus paths. So furthermore, it's not the wheel load, but rather the damage to the pavement caused by the wheel loads. So that is a primary concern. So that's why this selection of the load, so we decided to select these loads for loading the trucks on the bus paths to evaluate the performance of that and find the critical loads. As discussed, different load cases were identified and considered in this numerical model, including the dead load, the self-weight of the concrete slab, moving load of the trucks based on the AASHTO that explained in the previous slide, and temperature load. We also evaluate the fatigue performance of a structure after we're done with the analysis and I identified the problems. So the self-weight of the concrete, as I told you, was considered as a dead load and was uniformly distributed. So as a slab with a thickness of 9 inches with a normal weight concrete. So, okay. So in the final element model, we use the CSI SAP 2000 software package. So this was a software that we use, and the type of the model that we use, element that we use was shell elements to model the slab. So the material properties are based on the existing design of the bus pad in Baltimore. We consider those for the wire mesh and also the concrete materials. Regarding the boundary conditions, we also consider the Winkler method. The Winkler model basically is considering springs, linear springs, to mimic the soil. I mean, support that can provide, the soil can provide for the slab. So the subgrade and subbase basically were considered with these springs. So based on the type of the soil that we had a range of a reaction modulus, so which is called K, that we consider here as a 20,000 kilonewton per meter cube. So that number, 20,000 kilonewton per cubic meter, so was multiplied by the tributary area based on the mesh sizes. And that was assigned as a stiffness of each spring at each mesh intersection to the shell elements that were connected. So in terms of the load combination, we also consider all possible different scenarios. So with combining all of these load cases, and then we perform analysis using the software and present the results. Regarding the model geometry, the size of the mesh was based on the size of the bus pad that the Baltimore City now is using, and in terms of the width, you know, the length, and also in terms of the design, we consider the same reinforcement that Baltimore City used to design these bus paths. As you see here in the section, this is a plan, and this is the section A that is showing the location of the wire mesh with the size of them. So basically the thickness of the slab is about 9 inches, and the rebar wire mesh basically are considered to be placed at the top of the slab. So, and this is how we mesh the element and mesh the whole slab. So basically, by considering the springs as a support and boundary condition, we try to mimic the two-way slab, performance of the concrete boss pad, and because a one-way slab cannot be considered because of the length of this. So we try to, consider, and we saw in the results that the results are basically showing the moment in two directions. So that means the slab is actually is like a two-way slab, is performing like a two-way slab. So the finite element model consists of 2,125 nodes and 2,016 shell elements. And so we evaluate the shear forces and also the maximum bending forces. The bending forces are actually defined as a local moment, local axis moment, so which explain as M11 and M22. So M11 and M22 were used as a negative and positive moments in longitudinal and transverse axis. So in terms of the load combination, we use the load combination based on the AASHTO. At the strength and service limit states. And here you see the results, the critical results that we got for the different load combination. The load combination, I think the total load combination that we actually used in this study was around 131 load combinations. So that means 131 loading scenarios. So combining different loads, and also considering all of these load factors that are indicated in AASHTO code. So these are showing the figure A to D are showing the maximum critical load in transverse and longitudinal axis. So the longitudinal moment M11 that it shows the negative 5 Gibbs feet. So the negative 5 Gibbs feet basically is per unit length. So that means negative 5 Gibbs feet per feet. And then for the maximum positive moment, 8.25 was resulted for the longitudinal moment. So for the transverse moment, we got -3 in a negative, the maximum -3 and maximum positive 5 Gibbs per feet times feet per feet. We also try, because based on the observation, we found that most of these boss pads in Baltimore City suffering from the poor subgrade compaction, because once they try to replace the flexible pavement with the rigid pavement, so they have to cut out this asphalt and then try to compact that part of the soil, but that compaction is not a perfect compaction. And we try to see what would be the effect of the the soil compaction. So if, for example, the soil compaction was not as expected, what will be happening in terms of the increasing or decreasing the maximum moment that are basically the forces that we use for designing these boss pads. So effect of the springs or effect of the soil stiffness are reported based on the making a flexible boundary condition or rigid boundary condition that can affect the load distribution from the trucks or buses to the ground. So, and that is the way that we see the differences and the significant effect in moment reduction or increase in a moment. So when the subgrade is changing its characteristics. So as you see here, so by increasing the subgrade modulus, the moment will be decreased. So that means a good compaction can result in lower moment. So because that more uniformly distribute the load. And of course, if that is a, the good compaction, so we can see the result that's basically the surface crack can be controlled by this. I mean, as one item. Of course, there's other items as the materials and the reinforcement that we're going to discuss in next slide. So the figure A is showing the effect of the subgrade modulus or soil compaction in a negative moment, and the figure B is showing the effect on a positive moment. So the subgrade modulus has a direct relationship with the compaction, soil compaction. So by increasing the soil compaction, basically the soil density will be increased, and that will directly affect on a subgrade modulus that can increase the subgrade modulus as well. All right, so here are some of the observations that we had in this study. So as you see here, the poor subgrade compaction was observed, and basically the thickness, even the thickness of the slab that they try to cut that part of the flexible pavement with that subgrade is not very uniform, and is expected that at least they have some lean concrete to level the underneath of the concrete slab. Another thing that was observed was the crack that here you see. This is actually the concrete bus pad, and this is the asphalt pavement. So, and you see that this crack basically extended from here to here. So that means these can be something related to settlement, and these settlement cracks are not even related to the specifically for that location of the bus pad, but also probably because of some utilities or something that underneath of the the pavement can cause these cracks over the time. Another thing is basically the surface cracks due to the negative moment. As you see here, this is a bus stop, and this is a bus pad. And here is when where the bus is usually stops, and you see that these cracks usually happen almost after, almost very close to the rear tire. And as you see, this is a mechanism that we can explain the negative and positive moments that occurs when a bus path, when a bus passes the bus path. So the negative moment, as you see here, is obvious. We can see that. But the positive moment, it caused cracks that are basically underneath of the slab and are not visible. So these are more dangerous than negative moments, because at least we can see the negative, the effect of the negative moments on the surface cracks, but the positive moments cannot be seen. And all right. Okay, so for this, we basically try to identify a couple of bus pads and try to cut two specimens with almost similar dimensions in the longitudinal and transverse axis, and from a bus pad in Baltimore City. And then try to bring those to the lab and test them, see how much strength they basically have, I mean the flexural strength. And to evaluate the flexural strength and comparing with the critical load that we already applied on the numerical model, and then see what would be the result of this performance evaluation. So in terms of the reinforcement, this is what is basically provided in a drawing, but we observed that in most of the cases, the reinforcement that even was indicated in the drawings were not seen in actual construction. So sometimes the spacing between the rebar the wires were different from what basically was indicated. And another thing was, as I told you in the previous slides, so the rebar, the wire mesh basically are considered to be placed close to the surface, but in most of the cases, especially during the construction, so the concrete crews could walk through the reinforcement, and before the concrete is cured, so their placement is not as expected. So, and that can change also the performance of that. I mean, of course, for the shrinkage and temperature reason, that can be justified, but for the strength wise, so we can't justify that, because if that reinforcement goes near the neutral axis, so this is not something that we, as a designer, so we can expect. All right. So here is the lab and the test setup that we did in the lab, and for these two samples that we got from the actual boss pads. And then you see here the performance of these two beams, these two strips, I can say, was not as expected. And we compare the results with the design even, and with the actual required capacity in terms of the bending and shear, but none of them basically were met the requirement that we have. So here you see a test that we have done, for one of them, so I think it's the longitudinal one. And 3, 2, 1, go. This was conducted in Materials and Structures Lab in Morgan State. Oh, yeah. You're cracking. You're on the side. And as you see here, so we observed a sudden failure. And the sudden failure can be caused by two reasons. One is an over reinforcement, and the other is an under reinforcement. So for this case was under reinforcement, and concrete was basically failed, similar to a concrete section that has no reinforcement at all. So which is not desirable. Of course, it's not the building structure, but in terms of the minimum moment capacity, so we try to see and compare that with what we actually expected to have in terms of the critical, based on the critical load that we calculated in the computer simulation. All right, these are the results. So specimen 1 and specimen 2. So for the longitudinal strip, was almost close to the what we expected based on the actual design in Baltimore City. But for the specimen 1, so which was cut from the transverse strip. So that was very, I mean, the load bearing capacity was very low, and even less than, you know, what it should be based on the design, and based on the drawing that it was given by the Baltimore City. So one of the reasons of that was basically a lack of enough reinforcement, and some of them of these observation, based on the observation, we found that some of these are, you know, the spacing between the reinforcement is not as indicated in a drawing, and we found that, okay, so that is the main reason for that. So in addition to that, so many other reasons, including the quality of concrete, you know, the dimension of the section, all of those can incorporate to, you know, such a results that we see for a specimen 1. But now we want to see how we can compare that level of the bearing, load bearing capacity with what we have based on the critical load that we actually use, the 131 loading scenarios in our numerical model. So as I showed you before, so based on that 131 load combination and loading scenarios, so we found the most critical moments in negative and positive direction, and in longitudinal and transverse. And here are the results of the experiment for a specimen 1 and specimen 2. So which basically for the moments based on the Gibbs feet per feet is showing that 1.75 for specimen 1 and 5.58 for specimen 2. So based on the FE result, the positive moment, the minimum capacity should be 8.25, and the negative moment in the longitudinal axis should be 5. And for transverse, 5 and 3. So these are based on the computer simulation. So which is, I mean, as you see, cannot be accepted, you know, because the specimens are very basically designed. I mean, both design and construction are not, you know, meet the minimum requirement for the finite element results. Here are some scenarios that we try to improve the results, and for the crack, the moment crack, I mean, considering without reinforcement, the minimum of that section with the correct dimension and the perfect material, so should be around 5.54 Gibbs feet per feet. So which, as I told you in the previous slide, was not you know, seen in a specimen 1. A specimen 2, of course, was much better. And another thing was that for the shrinkage and temperature reinforcement, a minimum requirement of that, basically, we found that based on the ACI, even the minimum requirement for the temperature and shrinkage was not provided in the drawing that was based on the design. I mean, just regardless of the construction and the quality of construction. As a conclusion, the subgrade, based on the numerical and experimental studies, as well as field observation and design construction details, the findings are listed here, as you see. So the first one was subgrade. Subgrade settlement can cause much larger moment in the longitudinal and transverse axis of a boss pad than design moment. These cause concrete surface cracking and the slab failure in many of the boss pads observed in this study. Subgrade modulus significantly affect the moving load distribution and soil pressure, which consequently changes both longitudinal and transverse moment by up to 8 times. So that means a good compaction and perfect soil compaction can guarantee the uniform distribution of load and reduce the load, even if the design is not perfect. But a soil compaction can help to improve the design. Improve the slab performance or boss pad performance. The design and reinforcement placement is also another important part of the conclusion. So considering more realistic models for moving loads and boundary condition, the moment envelope and numerical model was extracted and shows that the boss pad experiences 49% larger moment in the longitudinal direction than the design moment. So placement of longitudinal wire mesh was considered to be close to the top face of the concrete slab, but based on the numerical results, the maximum longitudinal moment is positive, which requires reinforcement to be close to the slab's bottom. As per the site observation, the concrete clear cover was not the same at different places of the slab, which was caused by the concrete crews walking on the wire mesh during the pouring. This results in varying the slab's flexure capacity in different locations, which can cause the concrete surface cracks at the top and bottom face of the boss pad. Concrete slab failure due to the negative moment can be easily monitored and traced as a crack appear on the slab top face, but the failure due to the positive moment cannot be identified and monitored as easily because positive moment cracks initiate from the bottom face of the slab and are not observable. Therefore, more attention needs to be paid in designing the boss pad slab for positive moments. And regarding construction tolerances and best practice suggestions, so construction and placement of transverse joints were not properly performed. So in most of the cases that we observed, and these can initiate the cracks and propagate them to the next slab section. Poor leveling of the slab bed before the pouring of concrete was observed in the field during the construction, and that results in varying the concrete slab depth. So which can, directly affect the capacity of a section. These can exponentially reduce the flexural capacity of a slab in both uncracked and cracked section. As a recommendation, the subgrade compaction before the pouring the slab concrete is recommended. Using the different techniques, of course, is much more easier to compact the soil for a new roadway, but because of the condition of boss pads, so since the usually flexible pavement need to be removed and replaced with a concrete, so the subgrade compaction is really important, and we need to ensure and even test the subgrade to make sure that the compaction meet the requirement. In terms of leveling, the surface of the subgrade and underneath of the concrete boss pad must be completely level. It's recommended to take an additional construction steps to prepare a surface made of lean concrete with a thickness of 2 to 3 inches on the top of the subgrade to ensure the slabs underneath level and the slab concrete depth. Provide the rebar spacers can help to place the rebar, so in where exactly a designer supposed to see those reinforcement in concrete section. So in terms of the design, increase reinforcement for positive moment. So we have to increase that by 49%. Another thing is account for temperature and shrinkage reinforcement that was indicated in ACI 318. So another solution and recommendation is that adding the fibers, steel fibers or glass fibers or polymer fibers, basically can help to increase the flexural strength, because most of these failures that we found in the concrete boss pad, based on the surface cracks that they had, was because of the the moment. So that moment caused from the tensile strength in a top or bottom layer of the section, and adding the fibers to the concrete mix can increase the bending and tensile capacity and bending capacity of the section. So with that, we can address that. So this is a project that we started working on that with another agency that is from UTC, that we are working on that now. And recently, one of our projects that were funded by Region 3, so basically is using the recycled fiber steel extracted from the wasted tire in the concrete to enhance the property of the, the characteristic of, mechanical characteristic of the concrete bus pads, as well as, having the positive environmental impact, so by using the recycled material. So lastly, inspection during the construction and checking the tolerances are necessary to ensure the quality of the work, and they can guarantee durability and reduce the repair. Transverse joints must be appropriately placed and constructed and filled with the flexible materials to avoid the cracks development. As a future works, we have different area that we recommend for the future works. One of them is, design of construction joints, which are very important. Has not been paid enough attention in most of the design that we've seen here in Baltimore. And another thing is design for fatigue load. So we studied the fatigue load in our research, but because the strength was much lower than what what basically need to be, so the fatigue load cannot be evaluated because the strength is not enough to take the current load as a static load. Not even the fatigue load. So, but the fatigue load is another aspects that is considered as a future work. So we plan to do that. So we are now working on a new software. It's called Athena, so that can evaluate the can do the crack analysis and crack analysis of a concrete for different type of fatigue loads, and so that can help with design of these bus pad as well. And another thing is full-scale testing of the concrete bus pad. This is of course costly, but this is something that we can actually see the more realistic performance of a concrete bus pad if we can consider a test setup with the boundary condition that basically the concrete bus pad and soil provides. So we also would like to greatly acknowledge a sponsor of this research, Urban Mobility and Equity Center. And thank you so much for your attention. I would be happy to answer your questions.
Yeah. Okay. Dr. Mehdi.
Yes.
Yes, this is Anthony Saka. First and foremost, I really enjoyed the presentation. No, thank you very much. Yeah, my question now is basically, for me, it seems to me that we have two separate issues here. One issue associated with the subgrade, and the second issue actually, the concrete itself, the material, the material of the concrete itself. So my question is basically, first and foremost, a comment. We know that, of course, in pavement, if the subgrade is not really stable, then of course, then it becomes a very expensive design to kind of accommodate the load that you are designing for. So my question now is basically, as part of your study, did you find it like ways of optimal way of maybe treating the subgrade, at least to ensure better stability, other than ensuring just compaction, adequate compaction. Do you consider materials that can be used to treat the subgrades to ensure better stability?
Yeah, very good question. Thank you so much, Dr. Saka. Basically, I can categorize the causes of these failure basically on one for design, based on the design. Design basically is not, I mean, the minimum capacity that is considered in the design is not enough to carry the load. So this is the first thing. And the second thing is construction related problems. So the construction related problem, one of them is a subgrade, the other is the material properties, the concrete, the pouring and reinforcement, placing them, all of those that we discussed. So those are construction related. To answer your question regarding the subgrade, I would say based on the plots that I showed you that we studied, and we found that based on our numerical model, we showed a correlation between the subgrade modulus versus the maximum moment that is created in the boss path. So if we want to find a optimized number for subgrade, we need to look at the soil properties, because for different soil properties, we can increase the subgrade modulus up to a certain point, because those soil types, I mean, as you might remember, let me show you here. All right.
That's the building.
Yeah, so as you see here, this is the soil reaction that you see. So for the KS, by increasing the the reaction subgrade modulus, so we definitely can enhance the design, but the soil, the potential capacity of the soil to be considered as a loose soil, medium dense, or dense sand, or different type. Because, for example, if we have a sand, right, the only thing that we can increase that, we cannot increase the dense sand up to like 128, right? But changing the type of the soil from clay to sand definitely can help. If we have some specific type of soil in the location, so the solution to optimize that, if we want to change the soil to a different soil, I'm just replacing that soil and bring the new subgrade there, so which is basically very costly. That can enhance that. But with these plots that I showed you, where's that? Oh, yeah, here. So this is showing how we can, with a certain design. So for example, we were saying that now we have the actual moment capacity based on the design that we have, which is like 5, right? So with the 5, we have to have almost 100, 40 feet per feet cube, so subgrade modulus. But the problem is, we actually, in an actual site, we don't have that stiff soil. So I don't know if that answers your question.
Yeah, I'm okay. I'm fine. Thank you.
All right. Is there any other questions?
Thank you, Dr. Shukurian, for your great presentation. If there is no more questions, we can have Dr. Chavis to start her presentation.
Sure.
Hello, I actually have one question for Dr. Shukurian. This is Anam. If can you hear me, Dr. Shukurian? Are you still there?
Yes.
Yeah. Yeah, thanks for your presentation. I was going to ask, as far as, getting that sample you showed in your presentation, taking out those, large concrete slabs. So cutting that concrete in the field, does it impact, the natural strength of it when you bring it and test it? It doesn't make it, weaker?
Yeah, good point.
Yeah, that's a good point.
Very good point. Thank you very much. So yes, of course, that has some effect on the concrete strength, but usually even for concrete core, so that we take from the structures. So this is the only way that we can do that. So we have some rotary or maybe cutters that we can do that, but definitely we cannot neglect the effect of the sample preparing, to the maximum. But those are basically some micro cracks that might happen, with the help of the technology. They try to minimize those effects, but those are not something that we can quantify that, at least for now.
Right. Yeah. Thank you. So your client here was MTA, right? Not Baltimore City.
No, it was SHA.
Oh, State Highway.
Yes.
Okay. Because usually MTA builds this concrete slabs for bus stations, right, in the city?
So
yeah, but okay, then.
Yeah, please.
Yeah, usually no, yes, but under the purview of this highway administration.
Mm-hmm. Okay.